Okay, here we go. Let me adjust something else so I can see all you bright shining faces. Oh, there you are. I missed you guys. Okay, so we're talking about some limits. This is going to ramp up. The last thing in this slideshow is a little hairy, but we'll go slow, and I'll try not to use big words. So we're talking about limits, and we've dabbled enough into limits that hopefully you understand the general idea of what we're going to be talking about, but now we need to go a little more in depth. Okay, so we're going to focus on the early processes for finding limits before things get really crazy. We've talked about this already. As x approaches some value, what y value does it also get close to? We're going to look at it from a graphical standpoint and from a numerical standpoint. The worksheet you just worked on deals with the graphical aspects of it, but we're also going to talk about the numerical ways to find limits if, for instance, you don't know what the picture looks like. We're going to talk about what happens when it doesn't work, and we kind of dabbled in that a little bit, and then we're going to talk about some properties which are kind of simple. We're going to talk about the approach that I give you to find limits, and there's a set process here called an algorithm that you can use to find the limit of a function. And then, of course, you should be able to use those strategies. And then we're going to talk about the Squeeze Theorem, also known as the Sandwich Theorem, also known as the Pinching Theorem, because nobody can figure out what to call the stupid thing. And then, of course, you should be able to jam 20 grapes into your mouth without choking. Okay, anybody? No, I'm the only one. I'm the only one out of 30 of you who have jammed extra grapes in their mouth. Kids these days. Okay, what is a limit? We know that already. I've said it. What y value do you approach as you get close to an x value? So here's some function, and it's got a big hole in the center. We don't care what the value of the function is. We care about what value it approaches as you get close to a number. So if we look at something like 4, you can see that as the function gets very close to 4, it's getting very close to the value of 2. And in fact, it is exactly 2. So sometimes on a graph, that's going to be real easy. It is just going to be the value of the function. However, if we look at that hole there, if I approach the hole on the x value, there's no y to equal the function. But I can get really close to that y value, and that's what the limit is. I keep using the term approaching. As x approaches that weird number, what y value does it approach? Okay, so this function on the right is this rational function. And we talked a little bit about the notation, but let's talk about it again. The limit as x gets very close to 4 of this function. Okay, so you understand what we're doing here, right? I'll take that as a yes. Now, step 1 in solving any limit problem, plug and chug. Okay, so do that. Bust out your calculators, do the math, whatever. Plug 4 in there to tell me what this function equals. I'll wait.
You just have to plug in 4 into this equation, right?
Yep.
Because it's
nothing fancier than that. And then, of course, once you do that, you need to tell me what you get for an answer.
0.
Find.
Hold on, I heard 2 answers. What?
Undefined.
Why?
Because there's a 0 in the denominator.
Okay, somebody said something else. Alex, was that you? What'd you say?
Yeah, it was. I didn't solve for the denominator. I only plugged it in the numerator, so I got 0. So I was like, oh wait, then 0, but it could be undefined. So.
Noah, did you solve the numerator?
I did both.
You did both. Okay. So you got 0 over 0. Okay, this will be fun. This is for everybody. What does 0 over 0 equal? By the way, let's go with 3. 3 possible answers. Probably 4.
Infinity?
Okay, why?
I don't know, it's just a guess.
You were feeling it. You're in the infinity groove.
Yup.
All right, somebody else. Other possible answers.
Isn't it just undefined because you can't divide by 0?
That's 1. Can't divide by 0, therefore undefined is a possible answer. Good. What else? Well, actually 2, because we have Noah's infinity in there.
Are you saying like possible correct answers or possible answers?
Yes.
0,
Zero?
I guess?
0, because the numerator is 0. Good. And
1?
1. Why?
Because the number divided by itself will always equal 1.
Correct. Okay. Undefined, 0, 1, and infinity, just because you threw that in there. Which one's correct?
Undefined?
No, none of them. Or all of them. Yeah, that doesn't. Oh, Sarah, you look like your head's going to explode. Okay, that doesn't make any sense. We're going to table that for a while and come back to it. Okay, what it actually equals. What you need to know right now is that's bad. 0 over 0 is not an acceptable answer. Okay, so again, step 1, plug and chug. Okay, now what do we do? Any ideas? We could just quit. Doesn't work. By the way, DNE is a common answer there. Does not exist. Any other ideas? Let me give you a hint. What do you normally do with a quadratic?
Factor?
Ooh! Go ahead. Factor top and bottom. See what happens. I'll wait. Good practice, by the way. Rachel, what'd you find?
I'll do.
I'm sorry?
I'm still in the process.
Ah, gotcha. Okay. Anybody else? What happens?
I got. Oh, you can go.
Okay, I got, there's an x minus 4 on the top and on the bottom, so those would cancel out, but then there are 2 other values that are different.
Okay, beautiful. So if you did it correctly, well, I'm hoping I did it correctly. Did you get that?
Yeah.
Oh, beautiful. So we're all good. Okay. Caroline, what did you say canceled? There was an x minus 4 or an x plus 4?
Minus.
Okay, good. So those cancel. By the way, a little pre-calc review, that's where holes in graphs come from when those terms cancel. Okay, so step 1, plug and chug. We did that. We got 0 over 0. We argued about 0 over 0. That got us nowhere and frustrated all of us. So then we tried number 2. Step number 2 is always algebraically manipulate the function if you can. We did that. We factored the top, factored the bottom, canceled things, and now we're back to this guy. Step 3, plug and chug again. So plug in 4. That's That's 8, 15, 15 over 17. Did I do my math correct? Okay. Bingo, done. That's it. Stop. Plug and chug. Algebraically manipulate. Plug and chug again. And if that doesn't work, we're done. Okay. For now. Later on, we'll use some different techniques that'll allow us to go further. But for now, that's the 3 steps you're going to go through with any limit. Even in May, right before the test, when we're preparing for the test and a limit problem pops up, you're still going to go through those 3 steps. Okay? Questions so far? Good. Okay. So here's the notation that we used already. You should know this, but let me go over it anyways. The limit as x approaches a, and sometimes that a will be a c, sometimes it'll be a q, the variable changes, but it's some random value, of the function is equal to capital L. Capital L stands for the y value of a limit. Okay. Now what does that mean graphically? Well, we've talked about this already, but here's a nice little graphic representing what's going on here. As x slides closer and closer to a, then the value of the function gets closer and closer to L. So you'll see this is our A value, this is our L value, and as this moves that way like the arrows show you, that gets closer to that, and we can do it either from the right or from the left, and we hinted a little bit about how the right and left affect the outcome. Okay, so we good with notation? Problems? No? Okay. Good. Let's move on. What about this guy? By the way, this is one of our mother functions. Hopefully you know what that looks like. If you do know what it looks like, then sketch a quick graph of it in your notes. If you don't know what it looks like, then either fire up your calculator, fire up Desmos, fire up something, or that calculator app you have on your iPad, whatever, so that you know what that puppy looks like. It has an asymptote. Where is that asymptote?
Zero.
0. Perfect. Okay? So it should look like this. And I'm sure that you knew that, or if you didn't know it, you felt kind of silly when you graphed it, and you're like, oh, yeah, I know that. So we're okay so far. Here come the questions. What is the limit as x approaches 0 from the positive side? As I come from the right and the x value gets closer and closer to 0, what does the y value get closer and closer to? Don't be bashful.
0.
Nope.
Infinity.
Infinity, right. As I get closer and closer to 0, the function keeps going up and up and up. Does it ever get to infinity? Does it ever get to 0? No, because it's what we talked about with the approaching. It's approaching those values. It'll never equal 0 because that's bad, but it'll get very close. Okay, then in a lovely shade of red, what is the limit as x approaches 0 from the negative side of the same picture? Now I come from the left. What's it going to?
Negative infinity.
Hot diggity. Everybody good so far? Okay, then what's this equal to?
Wouldn't it just be negative infinity to infinity? Or negative infinity to 0?
Why?
0 to infinity?
Well, it's got to be a numerical value. It's got to approach a numerical value.
Would it be negative 1?
Nope. You understand the problem though, right? If I come from the right-hand side, I get one value. It gets very big. If I come from the left, I have another value. It gets very big. What if I don't come from either direction, or I don't tell you which way to come from? This becomes DNE. All right, and this causes a little bit of confusion with people because you're like, well, wait a second, why'd you get answers for the other two, but all of a sudden this guy doesn't have an answer? But again, when the two answers are different, then there's no value at the point. This is a fairly major limit theorem, and it says this. Because you know it's important, it's in a purple rectangle. The limit as x approaches a of f of x equals L, double-headed arrow means if and only if, that business. Okay, now what is that business? This might not make any sense to you whatsoever, so I wrote it in English. The left-hand limit must match the right-hand limit. Or there's no limit. Okay, so let's take that same idea and go. I know you're writing, but be patient with me. We're going to go back to the previous problem. Where's my picture? There it is. Okay, so now we look at this. There's no value with the circle. That's okay. As I approach from the right-hand side, I approach that value there. As I approach from the left-hand side, I approach that value there. And therefore, since the left-hand side equals 15/17 and the right-hand side equals 15/17, then at that value right there, it would also be 15/17. Now, that's not how you're going to do the problem because we did it by plugging and chugging and algebraically manipulating, but the same concept is true. In this particular case, the left-hand limit is equal to the right-hand limit, so we're good to go. In this mother function, that guy, it didn't work. The left-hand limit doesn't match the right-hand limit, so therefore there is no limit at the point itself. Does that make sense? Give me a thumbs up if so.
Is it because the... Sorry, go ahead.
Why does, in the other one, how do you know that the left hand and the right hand are both equal?
Because a couple things. Number one, because there's a value of the function at that point, for the limits, we're good to go. And also, you can see from the picture, they're both approaching the same value. Okay? Noah?
That was my question about approaching the same value.
Outstanding. 2 birds with 1 stone. Beautiful. Okay. We already saw an example of what happens when it doesn't work or when it fails. But, ooh, very exciting. I've been waiting for this all day. You know why? New mother function! Woo! Sorry, I'm excited. It's a new mother function. When's the last time you got a new mother function?
Algebra 2.
Yeah, there you go. You've been waiting 2 years for this. It's a new mother function, kids. Can I at least get 1 woo?
Woo!
Thank you, Noah. I know I could count on you. Okay, absolute value of x over x. If I get, in a perfect world, I would have given you the function had you figured it out yourself, but that would be silly because you just graph it. But it's not rocket science. If I put in 7, the absolute value of 7 over 7 is 1. I put in a gabillion over a gabillion is 1. So over there on the right-hand side, we're good to go. Hold on, let me get rid of that. Okay, on the left-hand side, the absolute value of -7 is 7 over -7 is negative. So we get this little thing going on. Okay, so now that we've got the mother function, let's talk about this guy. Before I break it down, let me just ask you a question. Well, I'm going to ask you a question which I have written right here. Why is it does not exist?
Because it would be dividing by 0 again.
Good. Why else? Yeah, so Jake, you're right. If I plug and chug, I get 0 over 0. The absolute value of 0 is 0. 0 over 0, that's bad. We can't algebraically manipulate it, so we give up the any. Good. Now, can you answer that question based on the graph? Why doesn't the limit exist at 0?
When you're getting it from the right side, you have different, like the left hand limit and the right hand limit don't match.
Well said, Rachel. So, if we want to get technical, we would say the limit as x approaches 0 from the positive of the absolute value of x over x is equal to uno. That's Spanish for 1. The limit as x approaches 0 from the negative of the absolute value of x over x is -1. And sure enough, the left-hand limit does not match the right-hand limit. Therefore, D and E. But who cares about that? We have a new mother function. It's right here. It's exciting.
Ooh.
Thank you. Okay, how are we doing so far? We're good? Anybody crying yet? You will later. Blah, blah, blah. What we already said. Yeah, great. Okay, good. Good. Yeah, we said that already. Good. Okay. Good. Ooh. It's in a blue box. Sorry, technically speaking, it's a blue rectangle. It's not a box. It's not three-dimensional. It's a blue rectangle. 3 things that are going to cause problems. 1, we've already talked about. 1 is just left-hand limit doesn't match right-hand limit. 2 is a fancy way of saying increasing without bound, and decreasing without bound is a fancy way of saying infinity or negative infinity. Whoa, easy there, killer. What happened? Let me try that again. Okay, so you might find the following discussion bothersome. Some people would argue that infinity is not an answer to a mathematical problem. That in those previous answers where we had infinity and negative infinity, those are not acceptable answers because infinity is a concept, not a numerical value. I would say that that's dumb. And we can argue about this later. I just wanted to give you a little heads up. Step 3, oscillates between 2 fixed values as x approaches c. That's weird. What does the word oscillate? Well, do you all know what oscillate means?
Yes.
My fault. Could you explain? I didn't ask the question. I assumed you would continue.
Like moving between, like moving away and towards one specific value.
Do you guys know what a paddle ball is? You know that wooden paddle with a ball on a rubber band and you just keep hitting it back and forth? And you know, your mom is really good at it and then the little ball breaks off and so she just puts that paddle in the kitchen drawer until you step out of line and then you get a paddle ball upside the melon? I'm sorry, maybe we didn't need to look at my childhood right there. That ball, as it bounces up and back, is oscillating in that scenario. You hold a spring with a weight on it, you pull the weight down and let it bounce back and forth, it oscillates. So we're going to look at an oscillating function. This is not very common. But it is something worth mentioning because it's one of those reasons that'll cause a limit to fail. Okay, so let's talk about these and how kind of common sense they are. If we have a function b, where b represents some number, so we have an equation like y equals 4. What can you tell me about the equation y equals 4?
A horizontal line.
It's a horizontal line. So no matter what x value I choose, it's always going to have a value of 4. That's what number 1 says. Okay, the limit of any horizontal line is just the value of the horizontal line. Number 2 is a fancy way of saying plug and chug. Put c in for x, we're good. 3 is, again, plug and chug. Okay. So again, blue rectangle from the book, not in English, steps 1, 2, and 3. In English, hopefully a little bit easier to understand. Okay, we good? Let me see what's next. Okay, let me finish this up and then we'll take a 5-minute break, okay? So this is, don't even bother writing this down because it makes sense and I can sum it up very quickly. It says, if I have the limit of a sum, a limit of the sum is the sum of the limits. The product of the limit of a product is the product of, so in other words, if I have the limit of f plus g, That's the same thing as the limit of f plus the limit of g. You can break that apart. Okay. You're not even really going to use this, but it's there and I can say you've seen it. And again, don't write the following down, but old school, we used to have to solve limit problems this way. You would take the limit, and you'd have to demonstrate, oh yeah, I know that the limit of a sum is the sum of the limit, so I break it down into those two. Okay. Then I'd look at the first one and say, okay, wait, I also know that the limit of a scalar times a function is the scalar times the limit of the function, and break it down that way. Well, then I would know that if I have the exponent in there, I can treat, and you go through all this business, and we would plug in the 2 there and find the limit of that, and then the limit of a constant is just the constant. That's the limit of b as x approaches b. So that just becomes itself, and then I plug the 2 in there because that's plug and chug. We talked about that already. And then simplify, and we get 19. This is ridiculous. What would you do? Well, what's the first step for any limit problem?
Plug and chug.
Plug and chug. 2 squared is 4, times 4 is 16, plus 3, 19. Okay. But this is a demonstration of these in motion. But you're going to plug and chug, algebraically manipulate, plug and chug again. Okay? Beautiful. Let's see. Let's stop there for a second. Let's take 5 minutes. I'll start my timer. You got 5 minutes. Knock yourselves out. Hopefully we can get everything in there. Go. All right, let's go. Everybody back? We good to go? You can hear me right? Yep, good. I'm not muted. Okay, so I chose the following example not because you need more practice doing limits, because we're going to follow the same procedure. It is good practice. However, something comes up in the next problem that you probably need a review on. Okay, so there's our problem. Ryan, what's step 1?
Plug and chug.
Attaboy. What happens when I plug and chug here?
You get 0, the denominator.
Keep going though. That's not enough. I do get 0 in the denominator, but...
And the numerator.
And the numerator. This is bad. No good. Ryan, what's step 2? What do we do next?
Factor.
Yeah. And this is the reason I chose this example, is because some of you may have forgotten how to factor the difference of perfect cubes. Anybody think they know it? No, of course not. I'd worry about you if you... Was somebody going to answer yes? That would worry me. Okay. So, quick review. A cubed minus B cubed. Oh, okay, hold on. I'm going to drop some math knowledge on you here. You all know what that means, right? What's it mean?
Plus minus.
Plus or minus. Do you have any idea what this means?
Minus plus.
Well, thanks, Einstein. How does it apply? Okay, I'll show you. This is one of those obscure things like one of those weird math things that nobody should really know this. Okay, but anyways, whoops. Okay, equals A minus B times the quantity A squared plus AB plus B squared. Changing colors. Unlike squares, the sum of perfect cubes can also be factored. A plus B times the quantity A squared minus AB plus B squared. Now, that chunk of math knowledge that I was going to share with you, you can do this. Now, nobody's really going to do that, but you can. That's mathematically correct. This means that if you take the plus, then that plus minus is plus. This one is the opposite of the one that you picked early. Okay? But realistically speaking, you're going to use the blue and the red one. Okay? Which means, as Ryan told us, step 2 is to algebraically manipulate. Now, here's something you're not going to like. Every time you're solving a limit problem, you need to write that pesky lim x arrow 1 until you get your final answer. X minus 1 times the quantity x squared plus x plus 1. All over x minus 1. Woohoo! Now, that guy in parentheses, well, hold on. This guy, get rid of this. Whoopsh, whoopsh. This thing left in parentheses never factors. So don't try. It's a waste of time. Ryan, what's step 3? Bring it home, brother.
Plug and chug.
Plug and chug. It appears I get 3. Woohoo! Okay, easy peasy. All 3 steps illustrated one nice problem, along with the kicker of the sum of cubes and the difference of cubes. Okay. That was fun, right? Good. Let's do something that's not so fun. I am not, for those of you that have had me for class before, you know I'm not a big fan of memorizing. However, these are two theorems that you're just going to have to write down and memorize. Now, why am I doing this? Because the time that it takes to explain where those come from, which is normally what I would do, is not worth it. They're not very common. They pop up occasionally, and you just need to have them. Flashcard worthy means, as we progress through the class, you might want to start generating some flashcards that are going to help you prepare for the AP test with fast facts on them and that kind of fun stuff. Okay? I'm going to move along a little bit faster, so I can come back to slides when we're done, but I want to get things done so we make sure to finish this stuff up before the end of the period. Okay, now how would I apply that? If I have something like this, as we've talked about, I would plug and chug first. The tangent of 0 is 0 over 0, gives me 0 over 0. It's no good. I algebraically manipulate. And how do I algebraically manipulate it? Well, the only thing I can think to do is I could rewrite this as the sine of x over the cosine of x all over x. Fraction within a fraction is bad. Whoops, 0. So then I would do the limit as x over 0 of the sine of x, a sine of x over cosine of x times 1 over x. Dividing by a number, same thing as multiplying by the reciprocal. Here's where I get sneaky. Match these two guys up and match that one up. So this becomes then the limit as x approaches 0 of the sine of x over x, which is legal because it's all multiplication, times the limit as x approaches 0 of 1 over the cosine. Oh, that's supposed to be, yeah. There you go, cosine of x. Okay. And that's supposed to be a multiplication, not a minus sign. First chunk we got on the last slide, it is 1. This, what's a cosine of 0? Ooh, that's kind of fun. What's cosine of 0?
1.
1. 1 over 1 is 1. 1 times 1, 1. Okay, easy peasy. How are we doing so far, kids? Okay. Now we're going to talk about, yeah, blah, blah, blah. Did all that. Great, great. Fantastic. Okay. This is where the fun stops. This is an important theorem. It doesn't happen very often. Solving problems is wicked. You have 2 of them on the homework in one of the next upcoming days. I would not be opposed to you just putting your pen down or your crayon or your stylus or wherever you're writing and just listen for a little while and see if you can absorb it like a mathematical sponge instead of writing frantically like a mad person trying to keep up. Okay. 3 names for the same theorem. I like the Sandwich Theorem. You'll see why in a second. So, here's our setup. Okay. I have 3 theorems. Sorry, I have 3 equations or functions. G of x, h of x, and f of x. You'll see that I've got this little chunk of information. So here's how I'm going to describe this theorem. I've got 2 pieces of bread. I've got a G piece of bread, and I got an H piece of bread. And I'm making a sandwich. Let's say a ham sandwich. Okay. So bread, and f of x is my ham. So we implement a little bit of lunch technology. When you make a ham sandwich, the ham doesn't just randomly come flying out of the sandwich. It stays between the 2 pieces of bread. You're with me, right? Unless you've got some different way of eating a ham sandwich, I believe my statement is accurate. Yes? Okay. So no matter what happens, that ham has to stay between the pieces of bread, which is verified by that statement. Okay. The ham, f of x, is always between g of x and h of x, which is the bread for the sandwich. Okay. Now, honest confession time, how many of you when you were a kid, or still now, would take your sandwich and mash it down? Haley, I see you shaking your head. Anybody else want to jump on? The rest of you don't have any idea what I'm talking about, or you're just afraid to confess it? You never took your bologna sandwich as a kid, chewed the crust off, and then put it down on your plate and just mashed it down. Yes? No. Unbelievable. Some of you need to get out more. Haley, I'm with you, girl. Did you ever then take that mashed down thing and fold it in half again so you get more meat?
No, I've never done that.
Woo! Take that for a test drive. Guarantee you're going to love it. Okay, so now I've mashed down my bread. Oh, look, and it mashed down to this little point here. At that little point, the ham doesn't just randomly fly out of the sandwich again. It's got to stay between the two pieces of bread. So no matter how much I mash my sandwich down, that ham has got to be inside the two pieces of bread. All of that lengthy discussion is an explanation of the setup for this problem. Are you good so far? Give me a thumbs up. Okay, so the theorem says this. I can't work with the ham. We're going to ignore, I don't know anything about this crazy ham. But I can work with the bread. And I can figure out the limit of the bread as I mash it down. Since the ham has to stay between the bread, if the breads approach the same limit, then the ham approaches the same limit also. So it allows us to find the limit of the ham by just finding the limit of the bread. Some of you look like you're about to throw up, but just bear with me. We'll get there eventually. Okay, so that's what all that says. And if you want to read that, that's great. Nobody really cares. The three names. Okay, and now you see why I like to call it the sandwich theorem. The squeeze theorem, you squeeze the sandwich. Yeah, whatever. Okay, so we're going to use this as an example. There are actually three functions in that picture. There's the top parabola, there's the upside down parabola, and there's that little function in between, which, by the way, that is what's called an oscillating function. That little function in between is actually x squared times the sine of 1 over x squared. Okay? And we're going to find the limit of that as it approaches 0. You pretty much know, looking at the picture, that the answer is going to be 0. But if it's oscillating, it never reaches 0. So we need to use the sandwich theorem in order to prove that. Okay, so this is the point where you probably just want to put down your pencil and listen. I need to find the limit of the sandwich by finding the limit of the bread, and therefore getting the limit of the ham or turkey or bologna or whatever your lunch meat of choice is. This doesn't work with peanut butter and jelly. Okay? It's got to be some form of luncheon meat. If you're a vegetarian, anybody vegetarian? You could probably use like zucchini, eggplant, lettuce, a couple options there. Okay. I'm going to do this problem backwards. I'm going to build the sandwich first. Okay? So I'm starting with this little, a lot happens, I'm hesitant to click on this, but a lot happens in this next click. Bear with me. Okay, so let me explain this. I started with this chunk of information. That has absolutely nothing to do with the sandwich theorem. That's just the definition of a sine function. You all remember, if you graph sine, it's always between 1 and negative 1. And it doesn't matter what you take the sine of. The sine of x squared is going to be between 1 and negative 1. The sine of pink elephants is between 1 and negative 1. So no matter what I put in there for t, it'll be between 1 and negative 1. Okay? So what I chose to put in for t is this, 1 over x squared, because that's what I need it to be in this problem. Okay? So the sine of that mess has got to be between 1 and negative 1. But that's still not enough because my entire function involves x squared. So I multiplied everything by x squared. And I get negative x squared is less than x squared times the sine of 1 over x squared is less than x squared. Okay? That should look familiar because that looks like, looks like this from our original function. Okay, so we've established the bread and the ham. So I don't care about the ham. It doesn't matter in my universe. All I care about is the bread now. So I'm going to find the limit. Where is it? Come on. Wait, hold on. Let me back up. I'm going to find the limit of the first piece of bread as x approaches 0. Well, that's easy. Step 1, plug and chug. Oh, we get 0. Then I'm going to find the limit of the second piece of bread as it approaches 0. Oh, it's 0. I've smashed down my sandwich. The top piece of bread approaches 0. The bottom piece of bread approaches 0. So what does that tell you about the ham? It also approaches 0. Done. Okay. Anybody throw up in their mouth a little bit on that one? Maybe it's just a little bit. Kind of one of those. Okay. So this blah, blah, blah implies that the limit of that mess equals 0. So this is an exception to the rule. Now, what I skipped is I still would have plugged and chugged. Okay, and you see right away I get 1 over 0, which doesn't work, so I have to algebraically manipulate. You can't do that, so then I switch to the sandwich theorem. Okay. If a problem like this comes up, it will clearly be labeled as a sandwich theorem problem, and you go through this building process. Okay? Again, we're going to have these occasional lessons here where things are trippy and don't make any sense and bother you, but it's just the nature of the beast. The good part is we're done. So here's again the summary of what to do. Number 1, plug and chug. Number 2, algebraically simplify. Number 3, I threw this in there. If you can, look at the graph. Graph it on your calculator. Use Desmos. Number 4, just guess. You could pray to the math gods if you'd like to try. And then the last step is to plug and chug again. If none of these work, then it's a DNE. However, once you give somebody the option to DNE, it becomes the fallback for everything. You look at the problem for 2 seconds. You can't solve it, DNE. You didn't get enough sleep last night, DNE. Okay. I don't like the number 7, DNE. You can't keep falling back on DNE. You got to do the work. Okay. And again, write down the problem and cry for those of you that need the help. Okay, I'm exhausted. That was a lot of stuff going on, and the bell's going to ring soon. So, before class on Thursday, please try to finish that worksheet. However, I will give you probably 10 minutes on Thursday to get back in your breakout rooms and either finish it up with your group or go over it with your group to make sure you got it under control. And then you have day 6 for homework. Questions, concerns, anything for the good of the cause? Outstanding. You know that 0 hours are always there, so if you need help, come into 0 hour and I will answer some of your questions. Other than that, we're good to go. Shut this down. Discard, stop recording.